Hey everyone, I'm about to sit down and do the Moment of Inertia practice sheet, so hopefully this helps you. Away we go. Number one is 4 objects are held in a position at the corners of a square by light rods as shown in the diagram below. The moment of inertia, I, of the system about the x-axis will be which of the following. So to get this thing started, let me go full screen here. Pen. Just regular pen. The moment of inertia, I, equals the sum of mr squared. I'm going to label these. Let's label this 1, 2, 3, and 4. So I equals m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus m4 r4 squared. I'm going to find out each of those values. Mass 1 is 3. Radius 1 is, it's 3 meters from the rotation axis. Don't worry about the diagonal, just perpendicular distance from the rotation axis. So that would be 3 squared plus mass 2 is 2 kilograms times 3 squared plus mass 3 is 2 kilograms times 3 squared plus mass 4 is 4 kilograms times 3 squared. And I think when you do it all out, you end up getting, I'm going to look at my little cheat sheet here, 99 kilograms meters squared. There's your moment of inertia value about the x-axis here. Going down the page, the next question is, what would the moment of inertia be if the rotation axis were about the y-axis? I'm going to be honest with you, that's a bad question because we don't know where that y-axis is. It would be very, very different if it were down the middle or through the 3 and the 2 or the 4 and the 2. I think a better question to ask yourself would be if the x-axis went through the, let's say, the 3 and the 2 kilogram. Then we would just have to change all our radii. So let's say, let's do the question. We'll say x-axis through the, sorry about the writing, 3 kilogram and 2 kilogram. So that would be like up here. So if that happened, we would say I equals, skip around a little bit, m1 r1 squared plus m2 r2 squared plus m3 r3 squared plus m4 r4 squared. Plug in the numbers. Mass 1 is 3, but the radius is 0 because now the x-axis is going through that point, so that actually has no factor. Mass 2 is the same thing, 2 kilograms but with 0 radius. Mass 3 is 2 kilograms and it's 6 meters away. So we're going to add now. 3 and 3 gives us a radius of 6. And then the final one is 4 kilograms at 6 squared. And I don't know what that is because I just made this up. So I'm going to use my handy dandy calculator. That's a Blue's Clues shot. 6 squared. 216. So I equals 216. At least that's what I got. I hope it's right. I think it's right. But so in that case, this would be harder. Part B would be harder than part A. Let's go to question 2. If the system in question 1 is set in rotation about the x-axis, the original, find the torque that will produce an angular acceleration of 1.5 radians per second squared. Well, Newton's second law of rotation is torque equals I alpha. And so if I want to find torque, it's already solved for torque. And I is 99, and this is 1.5. So torque equals whatever 99 times 1.5 is. It's 148.5 meter newtons. And there's number 2. That's a simple type of problem. Oh, here we go, the challenge one. A potter's wheel having a radius of 0.5 meters and a moment of inertia of 12 kilogram meters square is rotating freely at 50 revolutions per minute. The potter can stop the wheel in 6 seconds by pressing a wet rag against the outside rim of the wheel and exerting a radial inward force of 70 newtons. Calculate the coefficient of friction between the wheel and the wet rag. Well, just to get an idea of what's going on here, this thing is spinning around like this, and it has an angular velocity, initial angular velocity of 50 revolutions per minute, which you need to convert to radians per second. If you do that conversion out, you're multiplying by there's 2 pi radians in 1 revolution, and for the minutes, in 1 minute, there's 60 seconds. So you end up getting 5.24 radians per second. The time that it takes to stop is 6 seconds. So that might be useful. There's like some type of object here that may push inward with a force of 70 newtons. And what that's going to do is cause a frictional force that's going to slow this thing down. It's going to create a torque. We're really looking at this friction as applying a torque to decelerate the object, and the way to go through this is to say torque equals I alpha. It's a Newton's second law of rotation problem, and the torque that's applied is this force, 70 newtons, at it's the force of friction, which is perpendicular to the radius. So the radius times friction equals I alpha. That's providing the torque. That frictional force is just mu times the contact that occurs. So that's the force applied, and that equals I alpha. And we can actually solve mu. Get I alpha divided by R times F. And if you look at this, we know 3 of those 4 values. We know the moment of inertia, which was told to us, it was 12. We know the radius is 0.5. We know the force. The thing that kind of eludes us right now is the angular acceleration. However, we do know that the initial angular velocity is 5.24, and it decelerates in 6 seconds to a final angular velocity of 0. So what we can end up doing is use one of our kinematic equations to solve for angular acceleration. It's going to end up being omega f minus omega I divided by t. Omega f is 0 minus 5.24 divided by 6. The angular acceleration is negative 0.873 radians per second squared. And that negative isn't too important. It's not going to change the coefficient of friction, so we're just going to leave it out. We only want the magnitude here. So it's 12 times 0.873 divided by 0.5 times 70, and we're going to get a coefficient of friction of 0.299. There's number 3, the potter's wheel. And finally, number 4. 150 kilogram merry-go-round in the shape of a uniform solid disc of radius 1.5 meters is set into motion by wrapping a rope around the rim of the disc and pulling on the rope. Calculate the constant force that must be exerted on the rope to bring the merry-go from rest to an angular speed of 0.5 revolutions per second in 2 seconds. Well, it looks like that we have some rotational kinematics, and then we're going to get into the second law of rotation. But if we want to deal with the second law of rotation, torque equals I alpha, we're going to need that alpha value. So I'm going to go over here and think about omega F equals omega I plus alpha t. Solve for alpha. Alpha equals omega F minus omega I divided by t. And I want to get 2.5 revolutions per second from 0 in 2 seconds. So my alpha is going to be, I should be able to do that in my head, but I'm not going to chance it. 0.25 revolutions per second. But we got to get that into radians to deal with the second law equation. So let's see, 0.25 revs per second times 2 pi radians divided by, that's in revolution, that's 1 revolution, and then we get seconds. I think we're good with seconds. We don't need to do that. So what do we end up getting? Let's see, 0.25 times 2 times pi, get about 1.57, and that's radians per second squared. Revolutions per second squared, so I forgot the square. And then we're going to come over here. Now this is a force applied at a radius, so really this torque is Rf, and that equals I alpha. So force, we're looking for force, right? Calculate constant force. Force equals I alpha divided by R. Force equals, now what is I? Well, I for a disk is 1/2 mr squared, so I'm going to have to do that. So it's going to be 1/2 times 150 times what's the radius of the disk? 1.5. Square it times 1.57. That's our alpha value, angular acceleration, divided by the radius of the disk, which is, let's see, 1.5, let's see, a little slow. Do all that out. Let's see what we get. 0.5 times 150, 1.5 squared, 1.57, divided by 176.63. I think that looks good. 176.63 newtons. And that's a little bit different than the answer key that I put online. That was 176.7, but answer key online, I used the exact value here. I used the rounded value, but they're very, very close. So there's your moment of inertia problem set. I hope that doing the homework with me around helped a little bit. If not, you could always ask questions in class.